So good afternoon. We'll continue our lecture series on error correcting codes. So in the last lecture we began by looking at subspaces, how one would test for subspaces with examples, and then after finishing our discussion on subspaces we went on to talking about we made a comment that there was in a particular instance there was no difference between a subgroup and a subspace, and that is the case which applies to linear codes. So linear codes were introduced as examples of subspaces, but they also turned out to be examples of subgroups. Okay, so we briefly defined linear codes next, and then I went on to the linear algebraic notion of linear independence, and we went through a discussion by saying what does it mean and looking at examples. Then we went on to talking about spanning, and we had just got started talking about what it means for a set of vectors to span a space. So we will look at examples, and then we will put the two notions of linear independence and spanning together and come up with a basis. Okay. So that is the direction in which we are headed. Excuse me. So I have put down on the pad, I have put down a title for our lecture. So let me just put down a quick recap of what we have done. So we looked at test for a subspace, then we looked at linear codes, linear code definition, we looked at examples. Okay, so we looked at linear code definition and examples, and after this we went on to talking about the notion of linear independence, we looked at examples, and towards the end of the last lecture we talked about the notion of spanning. So let me just quickly go over our last lecture. So I will actually kind of zoom out, since the intention is just to give a quick overview. So we began by talking about linear codes and linear independence, testing for the presence of a subspace. Then we pointed out that we defined what it means to be a linear code. We showed that all the three example codes that we had worked with were in fact examples of linear codes, and then after that I talked about what it means for a set of vectors to be linearly independent. We looked at examples in different settings in 3-dimensional space with respect to the rows of a echelon matrix, in the vector space of polynomials. Then we started talking about spanning. So maybe I will just slow down a little bit here, so that because we need to pick up the discussion from where we left off here. So here on the topic of spanning, so a set of vectors is said to span a vector space if every vector can be expressed as a linear combination of these vectors. Okay. And whenever I define this set, I have allowed the set to potentially contain an infinite number of elements, although in all our applications the set will be finite. So in the case when it is infinite, what you really want is that in any particular instance, if you want to make sure that it is able to generate a certain vector z, then all that you will do is you will call upon a certain subset of R vectors. Okay. So whenever you take a linear combination, the linear combination will only involve a finite number of objects. However, the set from which that they are actually drawn can be infinite. Okay. So, that is a subtle distinction. And here is a picture which just gives you tells you what it means, what the notion of spanning is all about. And then this is terminology, this is explaining what we mean by linear combination. So, we will pick up the discussion from here, and I will switch to my notebook for this lecture. All right. So, there is another definition. The space spanned by a set alpha 1, alpha 2, alpha n is the set of all, and in brackets I will write finite set of all finite linear combinations of the form sigma C I j alpha I j is equal to 1 to r, where r greater than or equal to 1 is an integer, and where the C I j all belong to the f, which is the underlying field. So, this is the underlying field of the vector space. All right. Now, one comment here, I have used the word space, the space spanned. So, if whereas basically if you look at this, this is a set, right, it is a set, possibly infinite. So, why do I call it a space instead of a set? The reason for that is you can actually show without much difficulty that this space is actually a vector space. The word space is used since this collection actually form a vector space. And you can verify that as an exercise. Now, we will write, so we will use the following notation when we want to refer to this space. So, we will say that W is, we will put angular brackets and then we will put alpha 1, alpha 2, alpha 3 dot dot dot. So, this is terminology for the space spanned by. Okay. So, this is the space spanned by the alpha I. All right. Now, so here's a question. So, if this were in a regular classroom, I would pose this question to those in the audience, but you might want to think about it. So, what is the space spanned by the following set So, I have put down 6 vectors here, and these commas here are a little distracting. So, perhaps I will just remove them. Okay, so, we have 6 vectors here, and the question is, what is the space spanned by them? Now, strictly speaking, you cannot answer this question without knowing the setting. So, the setting, so let me just say that the setting in which I am asking you this question is the setting in which we are working inside the vector space F2. So, we are inside this vector space, and the question is, if you think about these vectors as vectors belonging to this vector space, then what is the space spanned by these vectors, right? So, what I will do is I will continue with my lecture, and I will come back and answer this, so that you have a few minutes to think about it. So, I will leave a blank page so that I can answer that. And now, let us go on to the next linear algebraic notion, and this will be our last linear algebraic notion. After this, we will get back to talking only about error correcting codes for some time to come. Right. So, the notion is that of a basis. A basis for a vector space is a collection of vectors such that one, the set is the set spans the vector space V. Okay. So, a basis is something that combines the two notions that we had introduced earlier. One is that of linear independence and that is the other one of spanning. Now, one comment here is that when you look at this and you see it for the first time and you see this infinite collection of vectors, you might feel uncomfortable, and I do not blame you for that. So, if it is making you uncomfortable, you can pretend that it is finite, because as I mentioned earlier, in all our applications the set will actually be finite. So, let us pretend, if you like, you can pretend that it is finite. Okay. So, there is a finite set, and this set I mean it is said to be a basis for the vector space if this set is a linearly independent set, and then it spans the vector space. So, let us look at some examples. Now, if your vector space is R3 plus R, if this is your vector space, then the following is a basis. And it does not take much effort to actually see that this collection of vectors is linearly independent, and then further it spans the space, simply because you can express any vector in 3-dimensional space as a linear combination of these. Okay. So, this clearly is a basis. Just one remark that whenever you have in the spaces Rn, vectors like these are called a basis of this type is called a standard basis. We will just make a quick remark here. This is called the standard basis for R3. And of course, as you might imagine, there exists standard basis for other higher dimensional spaces Rn as well. Okay. All right. Now, of course, this vector space is nothing but our familiar 3-dimensional Euclidean space. So, we can attach geometry to this. So, if you were to ask the question, in general, could you lay down a condition for a bunch of vectors to be a basis, and the answer is yes. So, more generally, any collection of 3 vectors in R3 with which do not lie on a plane through the origin is a basis. Okay. So, you can picture if these 3 vectors do not lie on a plane, then they form a basis. And of course, the standard basis that we introduced earlier merely correspond to vectors along the coordinate axis, and it is clear that they do not lie on a plane through the origin. Now, let me just quickly go back and answer this question that I raised earlier. So, the question was, how would you describe the space that is spanned by all of these, and hopefully at least some of you all got this. it is not hard to see just by inspection that if you look at each of these vectors individually, then okay, there is a small typo here. I hope this didn't throw you off. There is a typo here. So okay, so perhaps it wasn't a fair question, but the intention was that each of these vectors has even parity. So it belongs to the even parity code, and you can actually check that any even parity code can be expressed as a linear combination of these. And why is that? Because you can see that if you just ignore the first component and focus your attention on the last 6 components, you can generate by taking an appropriate linear combination whatever you like in those 6 components, and then the 7th component or the first one is forced. Okay. So from this it follows that this in fact the above 6 vectors form a basis for the even parity code. So the answer is the above collection of 6 vectors form a basis for the single parity check code. Okay. Now getting back to basis, we will look at some other examples, but just one quick note here. As you can see in this particular instance, even when you focus on 3-dimensional Euclidean space, there can be more than one basis. So certainly the choice of basis for a vector space is not unique, right. So as can be seen from this example, so as can be seen from this example, a given vector space can have multiple bases. All right. Another example, supposing you are looking at the vector space of polynomials. Okay. So then you can verify that the following is a basis. The polynomials 1, x, x squared, x cubed, dot dot dot, this set is a basis. Okay. And you can verify that it satisfies the requirements. Okay. So now I just want to go back and talk about this issue of finite versus infinite. So I told you that if you are uncomfortable with the idea that a basis is an infinite set of vectors, that you could think of it as finite. So now we will actually formally move on to consider to this restriction. So in fact you can actually divide vector spaces in, you can classify them as being either finite dimensional or not, depending upon whether they have a basis that consists of a finite number of elements. And our interest is mostly in finite dimensional vector spaces, in which case the basis will always have a finite number of elements. Okay. So let us make that definition. a finite dimensional vector space is any vector space possessing a basis that consists of a finite number of elements. And now we are ready to lay down a theorem. Let V plus dot be a vector space, be a finite dimensional vector space, and we will abbreviate finite dimensional by just f dot d dot. Then any two bases for V must contain the same number of elements. In particular, it is not possible that if a vector space has one basis that consists of a finite number of elements, that it can have at the same time another basis containing an infinite number of elements. Okay. So, in particular, finite dimensional vector spaces will always have a finite basis. Moreover, the number of elements in the basis is fixed. How do we prove that? Well, the proof actually will involve two lemmas. I will not prove the lemmas themselves because it will take us a little too far out. I will just state them, but we will use them to actually prove the theorem. The proof will make use of the following two lemmas. Okay. So, lemma 1, if a vector space V has a basis consisting of n elements, then any collection of let me just change this to m. I like to think of n as being greater than m, so let us put m here and let us put n here. If a vector space has a basis consisting of m elements, then any collection of n greater than m elements is a linearly dependent set. Right. That is the first lemma. All right. Now, I am going to use some electronic technology to actually make the next piece of writing a little bit easier. Okay, so my next lemma is very similar to the first lemma, so I am just going to make some changes. So, lemma 2. So, lemma 2, if a vector space V has a basis consisting of m elements, and I want to change this n to n, then any collection of m less than m elements cannot span the space. Okay. So, in the first case we actually said that supposing you have a basis that consists of m elements. So, there is going to be a pair of integers m and n. So, I am always going to think of n as being bigger than m in this particular case. So, the first lemma says that if you have a basis that consists of m elements and someone gives me n elements from the vector space where n is a larger number than m, then without even examining those vectors you can just simply say, well, that must be a dependent set. Okay, that is the content of lemma 1. Lemma 2 says that if you have a basis that consists of n elements and if someone comes with a smaller number of elements, then you can, without again examining them, you can say right away that this set cannot span the vector space. Okay. So, what these two lemmas, so I am going to skip the proof in both cases, and then I am just going to draw a conclusion from these two lemmas. Okay. From these two lemmas, it follows that a basis is simultaneously a maximal linearly independent set and B a minimal spanning set. Okay. So, it is maximal in terms of linear independence, but it is minimal in terms of spanning, right. So, now let us just go back and see where we were. What we were trying to do was we were trying to prove the following theorem. The theorem which says that if I have a finite dimensional vector space, then any two bases for the vector space must contain the same number of elements. Okay. So, now let us see how we can use these lemmas to prove it. So, proof of theorem. So, let alpha 1, alpha 2, alpha m and beta 1, beta 2, beta n be two bases for the vector space V. Okay. So, now you have two different bases, one seems to have m elements, the other seems to have n elements. Now, let us regard the basis consisting of the vectors alpha I as a kind of a reference. So, think of that as a reference, and then let us examine the vector set beta j in terms of this reference. Okay. So, then what it says is that, look, the alpha I are linearly are a basis. So, so they cannot be a linearly independent set whose size is larger than m, but the beta j form a basis. They must be linearly independent. So, it must be that n must be less than or equal to m, because after all no linearly independent set can be of size larger than m. Okay. Again, we are regarding alpha as a reference. So, that is with respect to the notion of linear independence. Now, let us switch viewpoints to the notion of spanning. Now, the alpha I again are our reference basis, and this reference basis contains m elements. So, if some other basis claims to span the vector space, it must contain at least m elements. From that point of view, n must be at least equal to m. So, you have these two conditions, n cannot be larger than m and n cannot be less than m. So, it has to be the same. Okay. So, that is the proof. Since the alpha I is equal to 1 to m form a basis and the set beta j is equal to n are a linearly independent set, it follows that it follows that n must be less than or equal to m. Okay, now again I am going to duplicate this page. Okay. Again, using similar reading, since the alpha I form a basis and the beta I span the vector space V, it follows that n must be greater than or equal to m. Therefore, n equals m and we are done. Okay, so that proves the theorem that any two bases must contain precisely the same number of elements. By the way, just a comment, there were two lemmas that we used in this proof, and I did not give you the proof, but the proof is basically based on linear algebra. Okay, so there is nothing very deep about it, it is just that it would take us too much time to actually go through the proof. Now, having established that, we are now in a position to actually define what is meant by the dimension of a vector space. The dimension K of a finite dimensional vector space is simply the number of elements in any basis for V. So, the dimension of a finite dimensional vector space is simply the number of elements in a basis, and this definition makes sense because we have already established that if you come up with a basis and I come up with a basis for the same vector spaces, and even though our basis may not be the same, it still is true that the number of elements in each of the bases is the same. So, we will come up with the same value for the dimension of this, and of course, this applies to the case of a finite dimensional vector space. We are not talking about those instances in which the number of elements in the basis can be infinite. Now, we have encountered examples of such spaces. Let us see if I can pull up a quick example. Yes. So, for example, if you look at the space of all polynomials, now that is an infinite dimensional space because it has a basis consisting of an infinite number of elements 1, x, x squared, x cubed, it never stops. So, that is an example of an infinite dimensional space. But as I mentioned earlier a couple of times, in this course, as far as applications are concerned, we will be restricted mostly to the finite dimensional case. Now, getting back to coding theory. Okay. So, with that we are done with our detour into linear algebra, and we are back in on our topic of error correcting codes. So, dimension of a linear code. So, definition: the dimension of a linear code C of block length n is simply its dimension as a subspace of the vector space f2 to the n plus f2 dot, right. So, that is what we mean by the dimension. Let us look at some examples. If we look at the repetition code, which simply consisted of the all 0 vector and the all 1 vector, then a basis. Now, this is a subspace of f2 to the 7. So, clearly a basis for this code is just the vector of all ones. Therefore, the dimension is equals 1. Now, just a quick note here. Okay, so, this is an instance and the code has block length 7 and dimension 1. Some notation. NKD code signifies a block code of length n, dimension k, and of minimum distance d. Now, it is important that when you write this down, we use rectangular braces. Okay. If you used curved braces, then that is usually reserved for the case when the code is not necessarily linear. So, that is 1. 2. Sometimes it may be that we do not know the minimum distance of the code, in which case we will simply write an NK code. Okay. So, let us actually make that note as well. So, then so in this case here an NK, simply an NK code signifies a code of length and dimension k, period. Okay, so, there is no mention of minimum distance, but again just note that we have used rectangular braces. All right. Now, there is an analogous notion for the case when the code is not necessarily linear. So, let me just again select the page. I am going to give you the definition on the next page. Okay, so what happens when the code is not necessarily linear? Then first of all, the braces change from rectangular to curved. Okay. All right, and then you do not use k. What is typically used instead is the letter m, a block code of length n. Now, dimension does not necessarily make sense if the code is not necessarily linear. So, we will actually say instead of size m. Okay. So, there is a big difference between capital M and K, because if the code is linear, then m is equal to 2 to the k in the case of a linear code. And analogously, when we do not know the minimum distance, we will just write n and we will put down n m code, a code of length n and dimension and size m. Okay. All right. So, now that we have got the notation straightened out, let us go back and see for our example code here. So, this repetition code now, let us take a look at what its parameters are. So, this code is now, therefore, you can see that the block length is 7. Since it has a basis consisting of a single element, the dimension is 1, and the minimum distance we know from earlier is 7. So, this is a 717 code, right. So, that is what it is. Next, let us look at another example. Let us look at the example of the single parity check code. Okay. So, now for this I am going to again go back, because we did a computation which will help us determine the basis. Once I find it. Yeah, so I want to select this particular set that we looked at. And come down here and I will paste it. Okay. So, here we have these 6 vectors. Now, the single parity check code, this is a basis for the code. Why is that? Well, what this example came up earlier in connection with spanning, and I pointed out that this set spans the single parity check code, but they are obviously linearly independent. So, this is a basis. So, as a result, this code has parameters 7, 6, and from our earlier computations it is a 762 code. Okay. So, and I think with that we are coming to the end of our time, so we will stop here. So, what we have done in this lecture is we have talked about the notion of spanning. We put linear independence and spanning together to talk about a basis. Then we talked about dimension of a vector space, dimension of a code, and looked at some examples. Okay. So, we will continue from this point onwards the next time, when the topic will introduce the notion of a dual code, right. Thank you.